we have a okay, good. So welcome everybody to the second session today. And in the session we'll see some really cool applications that build on lattice techniques and sort of borrowing from the obfuscation constructions. And the first talk is going to be by Venkata, who will tell us about lockable obfuscation.
Thanks, Sanjam. Can everyone hear me? I'll take that as a yes. Okay. Hello, everyone. Good morning, good afternoon, good evening, depending on your time zone. So this is going to be yet another talk on obfuscation. We've already had 5 wonderful talks on obfuscation. The title of this talk, we have 2 titles for this talk. We can either call it lockable obfuscation or VBB obfuscation for compute and compare programs. And the reason that we have these 2 titles is because this is based on 2 concurrent works. The first one is a joint work with Rishabh and Brent. And the second one is a work by Daniel Wicks and Yorgos Serelis. So for the rest of the talk, I will be discussing both of these works together. I won't make distinctions, which thing appeared in which one. Okay. So yeah, as I was saying, yeah, so over the last 5 talks, we have seen tremendous progress in code obfuscation. And by now, I don't need to convince you all that obfuscation is really awesome. We can build a lot of stuff from it. In all of these talks, we saw that if you can get obfuscation for all circuits, then you can do a lot of cryptography. And what's more interesting is that there has been tremendous progress in our understanding of the underlying assumptions for getting obfuscation or I/O for all circuits. So back in 2013, when we got the first candidate, we had obfuscation based on some exotic assumptions. But there has been remarkable progress since then. And as you saw yesterday, we can now build obfuscation on certain assumptions, which you can summarize in one slide. Okay. And hopefully, soon we'll have I/O from standard assumptions. And you'll wake up one morning, open ePrint, and you'll see a paper with the title I/O from standard assumptions. And that also comes with a good prize money. But for now, we need to manage with LWE plus something else. Okay. And for now, it's not clear whether we can actually build obfuscation from just LWE or standard assumptions. So we address this problem from the other end of the line. What we try to do is we try to anchor ourselves to standard assumptions, and then try to ask for what functionalities can we get obfuscation whose security is based only on the learning methods problem or other standard assumptions. Okay. So put more formally, I'm interested in the following question for the rest of the talk. What functions can be obfuscated using standard assumptions? And since this is a Lattice seminar, this will be the standard assumption that we'll use is LWE. So this question has received a good amount of attention over the last few years. And in particular, in fact, Ran Canetti showed how to get point function obfuscation for point functions even before we had the notion of or the formal definitions of obfuscation. And since then, we have had obfuscation schemes for things like hyperplanes and conjunctions. And in today's talk, we'll see obfuscation for a special class of functions called compute and compare programs. So what is this class of functions? So let me first describe this function class. So in this function class, every function is parameterized by a program P and a string alpha. Okay. And the program FP alpha works as follows. It takes as input some string X, it first performs a computation on the string x using the program p. So it computes p of x, and then it checks if p of x is equal to alpha. If p of x is equal to alpha, then it outputs 1, else it outputs 0. Okay. So let's see what we can capture using this function class. First, if you set your program p to be the identity function, that is, it takes any string x and just outputs x, then you can see that this exactly computes point functions. So recall, a point function is a function which is parameterized by a certain string alpha. It takes an x and it outputs 1 if x is equal to alpha, and it outputs 0 otherwise. And as I just mentioned, if you look at f with identity as your program and your string alpha, then this is exactly a point function which is parameterized by alpha. Let's make it a bit more interesting. Let's look at conjunctions. So recall, a conjunction is a function over n bits. And the function is defined as you take a subset of those bits and then compute an AND of either the bit or its negation. So in this case, for example, I have described this function f, which is x1 and x5 and not of x7. Okay. So there are multiple ways to define this program p and string alpha such that our compute and compare program captures this conjunction. Let me present one way of doing it. So the program p, I'll define it as follows. It takes n bits, x1 to xn, and just outputs the first and the fifth and the seventh bit. And I set the string alpha to be equal to 110. So now you can note that this conjunction f is exactly identical to the program f, which is parameterized by this p and this alpha. Okay. So hopefully by now you're comfortable with this notion of compute and compare. So let me make it a bit more complicated. So let's parameterize the functions by not by just one string, but by two strings, an alpha and a message. The alpha is used to check whether p of x is equal to it or not. And if it is equal, it outputs a message. If not, it outputs 0. Okay. So this is the notion. Yeah, feel free to ask any questions during the talk. In fact, let's keep this as interactive as possible. Okay. So this is the function class. What about security? So as I had mentioned at the start of the talk, we'll be looking at VBB security. In particular, we'll be looking at something called average case VBB security. And VBB roughly says that if you give an adversary an obfuscated code, all that the adversary can learn is just the input-output functionality and nothing else. And for this special class of functions, there's a much easier definition. And it's as follows. Intuitively, what we want is if you choose your string alpha uniformly at random or from certain distribution, then the obfuscation of p with the string alpha and the message should hide both the program p and the message. And this can be captured via a simple interactive game between a challenger and an adversary. So here's the game. The adversary first sends a program p and some message. The challenger chooses a random string alpha. And then it either sends an obfuscation of the program p with alpha and the message, or it sends an obfuscation of some garbage program. So when I talk about garbage programs, think of it as a program which always outputs 0. And the goal of the adversary is to distinguish between these two scenarios. So it should guess whether it got an obfuscation of the program p with lock alpha and the message, or whether it got an obfuscation of a garbage program. Okay. And if you're someone who likes giving names to cryptographic primitives, we have a name for this primitive. We decided to call it lockable obfuscation. And this is because we are thinking of the string alpha as a lock it checks whether p of x is equal to alpha, and then if it is, then it allows you to open the message. Okay, so for the rest of the talk, I'll be referring to the string alpha as a lock, and I'll be calling this lockable obfuscation. And as some of you might have already noted, that this string lock must be long enough. In particular, this should come from some distribution with sufficient min entropy. And why is that? Because if not, then the adversary can always win. Okay? So let me quickly illustrate. So let's say you had a single bit lock. Then the adversary could just send a program which accepts all inputs. And now if the challenger chooses this alpha to be equal to 1, then the adversary can distinguish, because if it receives an obfuscation of the program P, it can run it on any input X, it will get output 1. And if it receives an obfuscation of garbage, it will run it on any input, it will get output 0. So in this way, the adversary can distinguish if your lock is not long enough. But a thing to note over here is that if your lock is long enough, then if I give you an obfuscation of a program P with a random lock and some message, if this lock alpha is independent of your program, then even the honest user will not be able to evaluate this on any input X. So whatever input X the honest user tries, it will get 0. Okay. So as I've described it right now, it is not clear whether this thing can have any applications or not, because again, I want to stress on the fact that this string alpha that you choose must be independent of the program P and the message to get any sort of security. So in a nutshell, if I had to summarize how we're getting applications out of this, the main idea is that in the honest setting, this lock alpha will be dependent on the program P. But we'll first switch it in such a manner such that it becomes independent. And then once it becomes independent, then we can use the security of lockable obfuscation. So that brings me to our results slide.
Can I ask a question?
Yeah.
So,
yes.
So in some sense, this is similar in spirit to things like attribute-based encryption and predicate encryption, all these things, where in the security game there is no functionality or point obfuscation for that matter with random point.
Exactly right. Yeah, thanks Vinod for the heads up. Yeah, we will see attribute-based encryption, predicate encryption, and yeah, this is actually very related to what you just pointed out. Thanks. Okay, other questions? Are there any questions about the notion? I somehow cannot see the. Yes. Oh, there is a question. Why is there no trivial distinction between obfuscation of P and garbage? That's a good point, because I've chosen this. I'm not obfuscating the program P. I'm obfuscating the program P with a random lock alpha. Okay, and note that if you run, how do you distinguish? What is the trivial distinction? Well, you'll run it on some input, but with a very good probability, if you run it on some input X, then both programs will output 0. So I hope that answers the question. Okay, great. So let's see. Oh, by the way, I think whenever I switch to a new slide, I think it shows the number of pages, which it currently shows as 176. But don't be worried. I promise I'll finish this well before scheduled time. Okay, so bringing to our results slide, we show how to construct lockable obfuscation from learning with errors. And then we show a number of applications. The first class of applications is what I call upgrading security. And here we have 3 applications. The first one is making encryption schemes anonymous. This will be the focus of the talk. The next one is upgrading witness encryption to something called IO for rejected programs. And then finally, there's the application of making secure sketches private. And then we also have a second class of applications, where our goal was to replace indistinguishability obfuscation in certain applications with lockable obfuscation. So why is that useful? Because let's say you build something from indistinguishability obfuscation, then we don't have any instantiations of that based on LWE. But now if you replace IO with lockable obfuscation, then you get that thing from LWE. So here we have two applications or two classes of applications. The first one is called circular security separations. And the second one is called random oracle uninstantiability results. Okay. So let me now talk about the first application, which is making encryption schemes anonymous. Okay. So this notion was introduced by Bellare et al. In 2001. And okay, is there a question? Instead of having one alpha, oh yeah, that's a good question. So the question is, instead of having one alpha, can we have a list of alphas? And yes, if the list is constant or polynomial size, you can have this functionality. The cost is that your program size will, or the size of the obfuscation will grow with the size of the list. In particular, if you have, let's say, a sub-exponential number of alphas, then you cannot get a polynomial size obfuscation. Okay, so yeah, so the first application is which I wanted to talk about is anonymous encryption schemes. So let's first recall what is an anonymous encryption scheme. So a regular encryption scheme, you have a public key, and an adversary can see an encryption using public key PK, and the guarantee that we have is that this adversary won't be able to figure out anything about the underlying message. Okay, that is very useful. But let's consider a more general scenario where you have multiple users. Each user has his or her own public key. So here we have 3 users. Each one has a public key PK1, PK2, and PK3 respectively. And now let's say I send an encryption of a message to the 3rd user. So I encrypt my message using PK3. So the adversary, if the adversary sees this encrypted message, it does not know what the underlying message is, but maybe it can learn that this message is meant for the 3rd party. And in certain situations, this can be dangerous, and we want to avoid the adversary from learning this information. So even when it sees a ciphertext, it does not know which public key was used to encrypt the ciphertext. So as I mentioned, one of the applications of our work is to take any encryption scheme and to make it anonymous. So there was a question. Oh, it's been handled. Great. Okay. So how does this work? So first, note that here I'll be thinking of the decryption circuit, which takes 2 inputs. It takes a secret key and it takes a ciphertext, and it uses the secret key to decrypt the ciphertext, and it outputs a message or a reject symbol. Okay, so I'll think of this decryption as described as a circuit. So let's see how the anonymous encryption works. So I want to encrypt a message M using a public key PK. What will I do? First, I will choose a random string alpha, and then I will encrypt this string alpha using the public key PK. So note that I have not used the message that I originally wanted to encrypt. I have instead chosen a uniformly random string, and CT is the encryption of this random string. And now consider this program P, which has this ciphertext CT hardwired. Okay, so this takes an input. As input, it can take any string, and then it will try to decrypt this ciphertext CT using that input string. Okay. In particular, if you take the secret key corresponding to this public key PK and feed it as an input to this program P, then it will output alpha. This program P will output alpha. Okay, And the last step is to output an obfuscation of this program P with the lock value alpha and the message M as the anonymous ciphertext. Okay, so the ciphertext is a program, is an obfuscation of P, alpha, and message. How does decryption work in our anonymous scheme? Well, you're given a program and you're given a secret key. What can you do? You can just run the program on this input. So this is what the anonymous decryption does. It takes this program, the program which is the anonymous ciphertext, and then runs SK on this program. Why does this work? So recall our program P is this decryption circuit with the ciphertext CT hardwired. So note that if you look at the secret key, so SK is the secret key corresponding to this public key PK. And note that if you run this program P on SK, it outputs alpha. So what does that mean if you think about the obfuscation? If you run the obfuscation of P, alpha, and message with the secret key SK, then that should output the message. This is the correctness guarantee of our obfuscation scheme. So by the correctness, we can argue that if you run the secret key SK on this obfuscated program, you should get back M. And this is indeed what we want from a decryption. You want to, if you have the anonymous ciphertext and you have the secret key, then you should get back the message. Okay. Any questions about the scheme? No questions. Good. Okay. So next, we need to argue that this thing is indeed secure. So recall again, this is what was happening in the anonymous encryption. First, you encrypt alpha, then you consider the program P, which has the ciphertext CT hardwired inside it, and then the obfuscation is the anonymous ciphertext is an obfuscation of P with alpha and message. So at this point, one might be tempted to immediately use lockable obfuscation. But note that you cannot use lockable obfuscation yet because this program P is not independent of the lock value alpha. Why is that? Because this lock value alpha is contained inside this ciphertext CT, and this ciphertext CT is contained inside the program P. So in particular, this program P depends on the lock value alpha. Okay, so we cannot directly use the security of lockable obfuscation. But we can do something. We can do just one more step and then use lockable obfuscation. Anyway, so we have this anonymous ciphertext, and so let's say there's an adversary who claims that he or she can guess the public key given this anonymous ciphertext. Okay. So now consider a new encryption scheme where everything has a prime. So encryption anon prime, CT prime, and P prime. So what's happening here? Instead of encrypting alpha, you now encrypt 0. Okay, so CT prime is an encryption of 0. And then P prime is the decryption circuit, but it has the ciphertext CT prime hardwired inside it. And finally, you give out as your anonymous ciphertext anon CT prime an obfuscation of this program P prime with lock value alpha and the message M. Okay. So using the security of your encryption scheme of the underlying non-anonymous encryption scheme, using the security of this base encryption scheme, you can argue that these two ciphertexts will be indistinguishable. Okay. So which means if the adversary could guess the public key from an obfuscation of P, then it should also be able to guess the public key PK from the obfuscation of P prime. Okay, so this is what we have here. We have this adversary who claims that he or she can guess PK from this obfuscation of P prime, alpha, and M. Okay. And at this point, you should note that your string alpha is independent of your program P. That's because your program P now only depends on on CT prime, and CT prime is an encryption of 0. So program P prime is independent of alpha. So now you'll know what to do. You can use the security of lockable obfuscation to argue that the obfuscation of P prime is indistinguishable from the obfuscation of garbage. Okay. Is there a question? Okay, great. So now we have an obfuscation of garbage, and now because both the previous hybrids were indistinguishable, it means that the adversary claims that he or she can guess the public key from this obfuscation of garbage. But this is clearly impossible because there's no information of the public key PK in this obfuscation of garbage. So this concludes our security proof. No questions? Yeah, there is a question. Right. But okay, so that's a good question. The question is, in the previous hybrid, we gave the adversary more information. In particular, we gave the adversary information of M. So in this question is about this hybrid. So, but note that here we are we're not hiding M. We are using the NCPA securities over the string alpha, the encryption of alpha versus the encryption of 0. Good. So yeah, so this concludes our proof overview of how you can use lockable obfuscation to make any encryption scheme anonymous. But anonymous encryption schemes by themselves are not very interesting in terms of an application, because we already had these things from standard assumptions since the very beginning. It gets much more interesting when you look at more advanced encryption schemes. And it turns out that you can use the same methodology to even make advanced encryption schemes anonymous. In particular, we can do that for broadcast encryption and even for attribute-based encryption. So let me now talk about attribute-based encryption, since there we're not trying to hide the public key, but we'll be trying to hide something else. So first, let's recall what attribute-based encryption is. You already heard about this in Rotem's talk on Monday. So an attribute-based encryption scheme is a mechanism to have some more fine-grained control over your data. So here we have 4 algorithms: a setup, encryption, key generation, and decryption. The setup outputs a public key and a master secret key. The public key can be used to encrypt any message M for certain policy F. Okay, so the encryption algorithm takes a public key, it takes a message, it takes a policy F, and it outputs a ciphertext. The master secret key can be used to generate keys for attributes X. For any X, you can generate a key for this X. And finally, your secret key SKX will be able to decrypt a ciphertext CT only if f of x is equal to 1. If f of x is equal to 0, then this will output bot. Okay. So Rotem already told you why this notion is interesting. So the security, what do we want to hide? So let's say an adversary has an encryption of a message M for a policy F, and it also has a bunch of secret keys. It has a secret key for SK X1, X2, and so on to XQ. What do we want to hide? Okay, certainly we want to hide the message M, and this is the the most basic notion of attribute-based encryption, where if f of xi is equal to, or f of xk is equal to 0 for all k, then the message M should certainly be hidden. Okay. However, you may ask, what about the function f? It need not be hidden. Okay, so this is the base notion of attribute-based encryption. You might want something stronger. You might want to hide the function f. And that takes us to the notion of predicate encryption, where if f of xk is equal to 0, then the message M is hidden, and the function f is also hidden. Okay. And note that here I'm talking about hiding f even when the adversary can decrypt the ciphertext. So let's say f of xk is equal to 1 for some k, then the adversary can use skxk to decrypt the ciphertext. But we're saying that all that the adversary can learn is just the message and not the policy f. Okay? And it would be amazing if we could achieve this notion. Unfortunately, it turns out that this already implies obfuscation. So let's settle for something in between, which is sometimes called as one-sided predicate encryption. So here again, we want to hide the policy, hide the message M. Together with that, we also want to hide the policy F if the adversary cannot decrypt this ciphertext. In particular, if f of xk is equal to 0 for all k, then both the function f or the policy f and the message M are hidden. And note that again, if f of xk is equal to 1 for some k, that is if the adversary can decrypt some ciphertext, can decrypt the ciphertext using some secret key, then we don't want to hide the policy f. Okay. So this notion, the one-sided predicate encryption, can be interesting in certain settings. However, it turns out that it's pretty hard to construct these things. In particular, we have a number of constructions of attribute-based encryption. This is just a subset of the total number of constructions that are out there. But if you look at one-sided predicate encryption, we basically have just the analog of the work of Bonnet et al. This was shown by Gorbunov, Vinod, and Hotek in 2015. So using lockable obfuscation, what we can do is you can take any of these schemes on the left, basically just patch it together with lockable obfuscation in a similar way as to what I showed in the case of public key encryption, and that will give you a one-sided predicate encryption with the same properties. So this is all I want to talk about in terms of the applications. I'll check if there are any questions before moving further. No questions. Good. Okay, so now let's look at the construction. So the construction follows two steps. But before I talk about the construction, I want to quickly talk about how this notion of obfuscation came into being, like the behind the scenes of lockable obfuscation. Okay, so in my opinion, it all starts with this work by Allison, Susan, and Brent, where they construct something called two circular security separations. So this is some special encryption scheme where it satisfies in CPA security, but it does not satisfy something stronger called two circular security. So we want to construct an encryption scheme which satisfies in CPA but does not satisfy something stronger. So Allison and Susan and Brent showed a construction based for this based on LWE in 2015. Following that, there was a construction, two concurrent works showed how to extend this to something called as n circular security separations for any n. And again, here we want to construct an NCPA secure encryption scheme that is not n circular secure. Why do you want to construct these things? Well, it's mostly out of theoretical interest. But one other motivation at this point was that this was one of those things which we knew how to build from lockable or from indistinguishability obfuscation, but we didn't have any constructions based on standard assumptions. And these two works were the first ones to give constructions based on LWE. Shortly thereafter, in a joint work with Rishabh and Brent, we extended this to something called as bit circular security separations. And it turned out that underlying this bit circular security separation was already some sort of obfuscation going on. And this immediately led to the notion of lockable obfuscation. I think I saw a question over here.
You can answer that question at the end of the talk.
Okay. So I'll take that later. So this is the behind the scenes story of lockable obfuscation. Let us now look at the construction. So the construction goes in 2 steps. The first step is to build lockable obfuscation for low depth circuits or NC1 circuits. And the second step is to bootstrap such an obfuscator. So we have, let's say we have an obfuscator that can handle log depth circuits. We combine that with a fully homomorphic encryption scheme, and that gives us obfuscation for all circuits. And note that here we use FHE schemes with low depth decryption, and you already saw that in Hotek's talk on Monday. So let us first look at the second step, which is the bootstrapping step, since this is very similar to the application that I talked about a couple of minutes ago. So again, the goal here, you're given an obfuscator for NC1, you're given an FHE encryption scheme. And here I'll assume that this FHE encryption scheme is a secret key encryption scheme. That is, the encryption uses a secret key. The decryption also uses the same secret key. Evaluation, however, is public. There's some evaluation key, and using that evaluation key, you can evaluate any circuit, any ciphertext to, you can perform homomorphic evaluations on a ciphertext. So given these 2 tools, we want to construct obfuscation of a circuit C. This circuit C can be of arbitrary depth, and we want to obfuscate this with lock alpha. Okay. So let's see how to do that. The first step is to use your FHE encryption scheme to encrypt this circuit C. So you have some canonical description of this circuit C. We use FHE to compute an encryption of this circuit C. And then we need to use our obfuscator. So here's what we'll obfuscate. So consider a program P, which is the decryption circuit with SK hardwired. So this program takes as input a ciphertext, and the program decrypts the ciphertext using this secret key SK and outputs the decryption. So we will use our NC1 obfuscator to obfuscate this program with lock alpha. And again, why can we do this? Because this decryption is the FHE decryption, which can be done in NC1. Okay. So first, let us see whether this gives us correctness. So we have these 2 components. The first one is an encryption of the circuit. The second one is an obfuscation of this program. We want correctness. Correctness basically means if we want to be able to evaluate this program such that if C of x is equal to alpha, then this evaluation should output 1. So let me first describe what this evaluation is. So you have the homomorphic, you have the ciphertext. What you can do is you can homomorphically evaluate on that ciphertext to get an encryption of C of x. So given an input x, I can define a universal circuit with x hardwired, and then I can perform a homomorphic evaluation on this ciphertext with the universal circuit, and that will give me an encryption of C of x. Good. So now note that if you feed this encryption of C of x into this program, which decrypts using SK, then you should get back C of x. Okay, and in particular, if C of x is equal to alpha, you'll get back alpha. So if you run this ciphertext on this obfuscated program, then by the correctness of our obfuscation scheme, this should output 1 if C of x is equal to alpha, and it should output 0 otherwise. So this shows that correctness holds. What about security? So so note that we want to say that this encryption of the circuit C does not reveal the circuit C, because that is what we want to hide. We want to hide the circuit C. But you cannot just argue that immediately, because this secret key SK is also used in this obfuscation. But here, note that this lock value alpha is independent of this circuit, which is a decryption circuit. So you can replace that with an obfuscation of garbage using the security of your obfuscator. And once you do that, there's no information about this secret key SK in the obfuscated program. So you can safely replace the encryption of C with an encryption of garbage, at which point there's no information about the circuit C in the final hybrid. So using these two steps, we can argue that this obfuscation indeed hides the circuit C. Maybe there are a couple of questions. How complex is this homomorphic evaluation? Yeah, so good question. This homomorphic evaluation is not much more complicated than the circuit evaluation. In particular, if you have a circuit of certain size and certain depth, the universal circuit that runs on this will also be of similar size, except with certain logarithmic blow-up. And yeah, I'll take the other question about AB to one-side predicate encryption at the end of the talk. Okay. Great. So this is how bootstrapping works. So let us now get to the lattice fun part of this talk, which is constructing lockable obfuscation for NC1 based on the learning with errors assumption. So recall, this is what we want. We want to obfuscate this circuit C with a lock value alpha. And this circuit C is, outputs, let's say, m bits. The first natural step is to decompose this circuit C as m Boolean circuits. So each of these circuits C1 to Cm takes a certain number of inputs and outputs just a single bit. Okay. So now we want to obfuscate these m circuits C1 to Cm together with the lock alpha. And from Yale's talk, we know what to do with whenever we see a Boolean circuit of log depth, we know what to do with it. You just express it as a branching program. So let's say you have this circuit C tilde. You can express this. I'll take questions in a minute. So you can express C tilde as a permutation branching program of a certain length L, where the length of the branching program is roughly exponential in the depth of your circuit C tilde. But since C tilde has a logarithmic depth, the length of this branching program is polynomial. Okay. So each of these matrices, BIB, is a 5x5 matrix. And how do you evaluate this? So on any input X, you basically choose one matrix from each column, perform a product of those matrices, and we have the guarantee that the product is either equal to identity or some fixed permutation matrix. Okay. So in particular, if C tilde of X is equal to 1, then we have the guarantee that product of Bj Xj is equal to some permutation matrix, which I'll call P accepting. And if C tilde of X is equal to 0, then the product of these permutation matrices is the identity matrix. And for simplicity in this talk, I will assume this accepting permutation P accept has the following form. It has it basically permutes the first and the second position, but keeps the others the same. Okay. So I'll take a couple of questions at this point. There were a couple of questions. Looks like we got they're here. In the application of obfuscation. Okay, this is also related to the application of attribute-based attribute hiding. So I'll take this at the end of the talk. Okay. So again, yeah, recall this is what we have. We have this branching program. You take a subset product. The subset product is equal to this accepting permutation or the identity. So now we have these m branching programs, BP1 to BPM. We have this lock value alpha. And we want to obfuscate these such that for security, the obfuscation hides all branching programs BPI. And for any X, if you evaluate the branching program, each of the branching programs on X, and the evaluation matches alpha sub I for all I, then our obfuscator should output 1. Okay. Question. Where is the message? Oh, very good question. So here I'm talking about a simpler case where there's no message, it just outputs 0 or 1. But this same construction can be extended to handle messages. Good point. Yeah, thanks for bringing that up. Okay. So this is what we want. And so now I'll present a 3-step recipe for obfuscating these M branching programs together with a lock value alpha. So how do you do that? The first step is to choose a bunch of random matrices subject to the constraint that the summation mi alpha I is equal to 0. Okay. So this is very easy. What you can do is you can choose 2m minus 1 random matrices and set the last one depending on your constraint. Okay, so this is fairly simple. The next step is to encode each branching program BPI together with these two matrices mi0 and mi1. So first, this encoding must hide this branching program BPI. And secondly, the evaluation of the encoding, it should be possible to evaluate the ith encoding on any input x. And this evaluation should output either mi0 or mi1, depending on whether your branching program accepts x or not. So this is what I want from the from the encoding. So as some of you may have already noticed that these two goals are somewhat contradictory, because if you can evaluate on any input x and get m sub I0 or I1, that certainly leaks some information about the branching program BPI. In particular, for example, it can tell you whether two different inputs lead to the same output or not. Okay. So to relax that, I will make my goal slightly easier. What I'll do is I'll ask for, I don't want m sub I0 or m sub I1, but I'm okay with some matrix R sub x times mi0 or mi1. And this matrix R sub x is derived from the randomness that you use during your encoding. And another thing to note here is that this matrix R sub x does not depend on the index I. This is not a typo. This is by design. We want this matrix R sub x to be independent of your index I. And this will be crucial for our correctness. Okay. And finally, once you have all of these M encodings, you just output all the encodings. Okay. So the first step, the third step are pretty easy. The second step is where all the action is happening. Okay. So again, so let's see how this correctness works. We have these two guarantees. We have that the summation mi alpha I is equal to 0, and then we also have that the evaluation of the encoding on string x gives you R sub x times mi0 or mi1. What you can do is you can evaluate each of these encodings on input x. So as we know that the ith encoding takes you to R sub x times mi0 or mi1. And then what you do is you can add up all of these terms, sum them up from I equals 0, I equals 1 to m, and the evaluation outputs 1 if the sum is small. Why does this work? Because let's check if let's say the branching program evaluation matches the string alpha at all positions. Okay? So then this thing is nothing but R sub x times mi alpha I. And then if you sum them all up, note that this thing does not, R sub x does not depend on your index I. You can take that out. And once you take that out, this sum is equal to 0. Okay. So if this is 0, then these are closed, then even this thing must be small. Okay. So this is our, this is how correctness works. So which means that since the first step and the third step were pretty simple, it suffices to just focus on this encoding of the branching program BP together with these two matrices M0 and M1. So note that I have now gotten rid of the indices I from here because we just focus on one branching program. Okay, so why does this help? It looks like this goal is not very different from what we started off with. But these matrices and permutation matrices are really friendly objects. And as you saw in Yele's talk just an hour ago, you can use the GGH15 encoding to take care of this. In particular, recall what Yele talked about. So if you have some secret matrices S1 and S2, you can encode them into matrices D1 and D2 such that they satisfy this relation, that A0 times D1 times D2 is equal to, or it's close to, S1 times S2 times A2. And you can use this for also, again, Yele talked about this, you can use this for taking subset products. So let's say you have 4 secret matrices, Si0, Si1, or S10, 20, 11, 21. You have a matrix A2, and on the right you have A0 and DIB. As Yele described, if you take any subset on the left, multiply it with A2, it's roughly close to multiplying A0 with the same subset on the right. Okay. You can do this for multiple subsets. So here's what we'll do. We'll take the branching program, which has all of these permutation matrices. We'll encode each matrix into GGH15 secrets. So how do we do that? So first, recall, this is what we have. We have the product of BIXIs is equal to either this accepting permutation or this identity matrix. Okay. Now let's say I multiply this on the right with a vector Z0, Z1, and some random stuff. What do you get? You get you either get Z1, Z0 random stuff, or you get Z0, Z1 random stuff. The thing to note here is that the first entry of this product is either equal to Z1 or Z0. In particular, if the branching program accepts X, the first entry is equal to Z1. If it does not accept X, the first entry is equal to 0. So this is close to what we wanted, except we wanted to do this with matrices. Okay? So what do you want to do? What do you do when you want to get this behavior for matrices? Well, you just multiply or you tensor everything with identity. Okay? So now, in a similar way, if you look at the product of BIXI tensored with the identity, and then you look at the first block of this product times M0, M1, and some random stuff, then you either get M1 or M0 if depending on whether the branching program accepts X or not. So it looks like this thing should help us at least get our functionality working. In particular, what we'll do is we'll set our GGH15 secrets to be these matrices. Okay? S sub IXI is nothing but BIXI tensored with identity. Okay. And then once we have the GGH15 secrets, we know how to go to encodings. Recall, this is what we did in Yele's talk. These DIB matrices are just AI minus 1 inverse of the secret that you want to encode together with some noise. Okay. And finally, I will be giving an encoding of M0, M1 and some random stuff. I'll just output A2 inverse of M0, M1 and that vector. Okay. So we want to first check that this evaluation on X indeed gives us M0 or M1 depending on what behavior we want. And this is easy to check. Again, you use the subset product methodology to note that, okay, so note that we have this relation that say S10 times S21 times A2 is close to A0 times D10 times D21. So now you multiply on the right of both of these with A2 inverse of M0, M1, and some random stuff. And because these matrices A2 inverse are small, these two products are still close to each other. Okay, and note that what we have on the left is nothing but this product of SIXIs times this M0 M1 vector. And then if you look at the first block of this, you either get M1 or M0. Okay, good. Which means this evaluation works, but what about security? Does this encoding hide the ith branching program? Unfortunately not, because we are certainly revealing the final output, so that leaks some information about BPI. So how do you fix this? It's pretty simple. Instead of encoding BI, this BIB tensored with identity, you just tensor, instead of the identity, you replace with some random low norm matrix. Okay. So this is the summary of our construction. We first encode these branching program matrices into these GGH15 secrets, where each of these is a BIB times not times, tensored with some low norm matrix. And once you have these GGH15 secrets, you can encode them using GGH15, and you also give out A0 and A2 inverse of M0, M1, and random stuff. Now the question is this thing secure? And at this point, before I get into security, I'll look at the questions. Okay, there's a question, why is A inverse small? And this is because we are not talking about the traditional matrix inverse, but rather this is the inverse that's computed using lattice trapdoors. So Shweta talked about it in the first bootcamp workshop, and even Yele talked about this in the previous talk. All of these matrices A2 inverse are not matrix. This is not equal to A2 inverse times this vector B, but instead this is computed using something known as lattice trapdoors, and that guarantees that this thing is short. Okay, so this is our.
So Venkat, just a heads up, there's like 5 minutes left. So
yeah, that's great. Yeah, thanks. Okay, so what do we want? We want to argue that if M0 and M1 are random, then the distribution on the top looks like the distribution on the bottom, where we replace all of these DIBs with some random low norm matrices. Okay, and how do we do this? The first step is to use the GPV result, which says that if you look at A inverse of a uniformly random thing, then that is indistinguishable from a random low norm thing. In particular, note that these M0, M1, and all of these vectors are, or all of these matrices are uniformly random. So you can say that A2 inverse of this random thing looks like a low norm matrix, which is here. Good. So we have this now, and we have our encoding D2B, which is A1 inverse of something. Now we want to argue that these D2B matrices also look like short low norm matrices. And the way to do that is we'll first replace this thing inside A1 inverse with something that's totally random. Okay? And in order to do that, we need something known as permutation LWE, which was introduced by Canetti and Chen. And what this is a variant of LWE, which says if you take any permutation matrix P and you look at the following two distributions. The first distribution is you output a random matrix A together with P tensored with R times A plus noise, where this R is a random low norm matrix. Then what this result says that this distribution looks like two uniformly random matrices. Okay, so I'll illustrate why this works using a quick example. So let's say you take this permutation matrix and tensor it with R. And now we want to see what this matrix times A looks like. So you can decompose this matrix A as A1, A2, A3, and A4, and then check that this product is indeed R times A3, R times A4, R times A1, and R times A2. Now, if you add some noise to each of these terms, then you can use a traditional LWE to argue that each of these is indistinguishable from uniformly random. And another important thing to argue here, or to note here, is that this only works for permutation matrices. In particular, if you have this non-permutation matrix, then clearly this thing is not looking like a uniformly random matrix. Okay, so we are close to the end. First, we switch this matrix with a random thing using this permutation LWE mechanism, and then we can replace this using GPV to random low norm. Okay, so once you do that for D20 and D21, you can do the same for D10, D11. And if you have more levels, you can keep doing this. Cool. So this is what we wanted. This was our 3-step recipe. Okay, and are we done? I wish I had more time to let you think about this, but unfortunately, we're not done yet because this requires these matrices mi0 and mi1 to be uniformly random. And these matrices are not uniformly random because they are constrained by this constraint at the top. And how do we take care of this? Well, if the number of branching programs, then this m value was large, if this was much larger than some polynomial in the input length and the branching program length, then you can use leftover hash lemma. What if not? What if you had, let's say, a shrinking circuit? So the easy fix to that is to take some injective PRG, put the PRG on the top, and now your lock value becomes equal to PRG of alpha. So this is how you handle this, and once you do this, then you're done. And this concludes our construction. You might be tempted to ask, well, we could not handle permutation branching programs here. How do you do that? So for that, you'll have to read a follow-up work by Yile and others, where they had an interesting approach to fix this these encodings. Why does this look like random low norm? Well, you'll have to listen to Rishabh's talk for that. And yeah, so this is just I'm almost close to the last slide. Okay, so this is what we showed. Follow-up works have shown a number of other applications. Rishabh will talk about this thing called mixed functional encryption. There have also been interesting applications for zero knowledge. Some immediate open questions. First, I feel there should be more applications over here. So this is something to look into. Second interesting question is whether we can allow some sort of leakage on the auxiliary information or some. What happens if you output the lock together with your obfuscation? And finally, so as I did not describe what evasive circuits are, but this thing is a subclass of evasive circuits. Can we get obfuscation for other evasive circuits? Yeah, that would be interesting. So finally, we are almost at the end. So this is Yile talked about these different views of GGH15. I want to conclude with that. So note that this is what we had. So we have these two circular security separations, and we have GGH15, and both can be seen as some sort of being inspired by GSW13 homomorphic encryption. We derived this n circular security based on the two circular security. Around the same time, Zvika and others showed how to obfuscate conjunctions based on the GGH15 route. Then we showed how to get bit circular security. Yile and Ran showed how to construct private constraint PRS from GGH15. And then finally, we had lockable obfuscation. In hindsight, it turns out that all of these things can be instantiated using GGH15. But I feel there's some fun in doing all of these things directly. And yeah, I'll conclude my talk at this point. Thanks so much for your attention.